Now, okay, recording. Okay, so pre-activity, you do this before class or whatever. You can schedule out your days. There's some tips here, whatever. My tips are make a formula sheet. If you guys took Math 103 last semester, you guys actually could have a formula sheet to use. But in this case, you don't have any open notes, but it still helps to make that sheet so you know what you need to memorize. So you can just memorize one sheet and then you're good to go. Redo all the focus sessions. I feel like a lot of the exam questions are really based on the focus sessions. So like the only material I've seen are focus sessions and I could do all the exams. So just if you do those, I feel like that gives you a pretty good review of everything. Do the practice exam that's on the course website. It's kind of long, but get through it. It'll help you. And you can redo old quizzes and tests. So that's just some material for you to do. Do whatever works for you, but here are my tips. Okay, in this class, if you're in doubt, it is a trick. He is out to get you, I swear. It's terrible. But when in doubt, if you're like, I'm not sure, it's false, okay? Like, it's what you're not sure about. Here is, like, we're gonna see a couple examples at the beginning, especially with multiple choice. It sucks, guys. Not gonna lie. Okay, so suppose a of x is a function with a double prime 5 equals 0, then a of x has a point of inflection at x equals 5. Well, if you guys remember, if we have a function f of x, when f prime x equals 0, we think critical points. That's like maximum, minimum. When f double prime x equals 0, we think inflection point. That's where it changes from concave up to concave down or vice versa. So those are in both relation to the original function. So it's a critical point of f of x, inflection point of f of x. All right, so here you would think that you would have a point of inflection at 5. But remember, it's probably a trick. So there's one key thing you have to do with points of inflection and critical points, and that's to check the boundaries, to do like the derivative test or whatever, where you draw the number line, you put in 5, and then you check, is it like positive, negative on either side? So they don't give us the original a of x formula here. So we can't really do that test. So we're not completely certain that we have a point of inflection. We might have a point of inflection there because it equals 0. So that tells us that our thing is like changing, like the tangent line is linear there. There we go. That's the word. Our slope is linear there. So we know that there we have our second derivative equal to 0, but we don't know that it's changing from concave up to concave down or vice versa. It might just be going like concave up to like more concave up, if that makes sense. And so like that might be your point, but we don't know for sure that it's a point of inflection. All right, so to know that it's a point of inflection, we have to do this test with the number line, but we can't do this test with the number line right now because they didn't give us the original function. Therefore, this is false. Okay. Number 2, the population of a species of bird on a small island is modeled by b of t equals that. Given this model, we expect the long-term population to approach 250. All right, so this we have to realize is a limit. This is more like the beginning of the semester. Long-term population. The population is modeled by b of t. Long-term, you think t is going on to infinity. Long-term, when t is increasing, right? Our time in t, years, whatever, going on and on and on. All right, so once you realize that you're taking a limit, you can set it up like limit t approaches infinity, our years approach infinity, of 50 over 0.2 plus 1.05 to the power of negative 0.1 times t. So what you want to do is plug in an infinity for t. All right, so this takes some thinking, and you can use your calculator to help you on this one. That's what I like to do when I'm not sure. So we want to figure out what is that like section that has the infinity in it. I will highlight that, the section right here. What is that gonna end up being? Let's ignore the other two numbers for now and just focus on that. So if we have 1.05 to the power of negative 0.1 times infinity, what is that going to equal? Obviously, we can't really put that in our calculator because we can't put in infinity, but we can kind of think of it like, okay, 0.1 times infinity is still infinity, right? So this is still equal to 1.05 to the power of negative infinity. All right, so our exponent is negative, and it's getting larger and larger. So if we think of this like putting it into a fraction form, because I don't really like having negatives in my exponents, when we have a negative exponent, we can switch the sign, or like with any exponent, we can switch the sign and move it from the numerator to the denominator or the other way. So in this case, this is equal to 1.05 to the power of infinity. Right, so that's what our negative exponent is telling us. All right, so 1.05 to the power of infinity. When you're increasing the exponent, that number is getting bigger and bigger and bigger and bigger. You can also put that in your calculator. So you can do 1.05 to the power of 100, then 1.05 to the power of 10,000. Well, we get some arrows after a while. But you can see that this number, if you just keep on putting larger numbers, it's getting bigger and bigger. All right, so I can kind of say that like it's 1 over infinity. All right, so we're taking some liberties here. But 1 over infinity, when our denominator is getting bigger and bigger and bigger and bigger, we're getting closer to 0. So if we have a denominator of infinity, we can basically say that's equal to 0. And then I have a question here for question 1. Is it false because we can't necessarily prove that it's a point of inflection based on the info provided? Yes, exactly. Precisely. Okay, so for this, that like highlighted portion is basically equal to 0. So we have 50 over 0.2 plus 0. All right, so basically I just put in infinity and see what I get. There are like a bunch of ways to go about that. That's one way you can go. You can even just put in like 1.05 to the power of negative whatever 10,000 and then make it bigger and bigger and bigger, and eventually you will get 0. Okay, now this is really easy. We just divide out. So 50 divided by 0.2 gives us 250. All right, does that match? Approach 250. Yes. Do you guys see any tricks? I don't think so. It seems to all check out to me. I think we did all the proper steps, has all the right information. So I'm going to go with true. All right. So make sure you know how to do limits approaching any number, especially infinity. I feel like those are tricky. Definitely takes a lot of time to understand. So go back and review that if you're a little confused, but definitely know that. All right, next up, if marginal revenue is greater than marginal cost at a certain production level, then profit is increasing, and an increase in production by 1 unit will increase profit. Okay, so this was definitely in a focus session. They kind of gave you these rules, like when revenue is greater than cost, when cost is equal to revenue, when one's greater, like whatever. They had the rules, and then it tells you, should you increase production, decrease production, blah, blah. I probably wouldn't memorize that. You guys don't have the headspace for that. It's kind of useless information. When are you going to use it? Probably never. But if you just think about it here, revenue is the amount of money you're getting per item. I'm selling it for a certain cost, and then that money minus the cost it took to make it is my revenue. Maybe not. Wait, revenue is the money I get from it. Cost is how much it costs for me. That's simple. Let's leave it at that. Okay, revenue is the money I get for selling the item. Cost is the amount of money I put in to make the item. Cupcake cost me $1. I sold it for $5. Okay, so revenue is greater than cost. When revenue is greater than cost, then profit is increasing. Well, that's correct because profit is the revenue minus the cost. So the profit is how much I'm actually making off of it. And an increase in production by 1 unit will increase profit. So if I increase production, if I make more of them, then I am going to increase profit because I'm getting more money than I'm spending. So I want to keep making because that's a good thing. I want to keep producing these items so that I get more money overall. So that is true. You can go back and review the focus session too. I'm pretty sure they had like those rules there, but I would try to understand those rather than memorize them. It's just really not worth memorizing. Okay, here we have an integral. Okay, so this one is like another trick question, right? If we take the integral of 3x squared plus 5, we would get x cubed plus 5x. I would probably say true, but we're definitely missing something. Okay, this question is too easy. They're not going to make it this easy. So what are we missing? Anyone want to type it in the chat? Great, guys. The plus c constant. So we're missing plus c. Whenever you take an integral, never forget the plus c. So commonly missed is the plus c. Okay, so this is then false. Right, so this is so easy to get wrong. Just make sure you're on the lookout for that. Just like, if it seems too easy, it probably is. Look for the trick. Okay, suppose f of x equals a x squared plus b cubed, where a and b are constants. Then f prime x equals 2ax plus 3b squared. Okay, so basically we want to take the derivative of f of x. So what's important here is you realize, I'm going to draw it kind of differently. We have a x squared plus b cubed. We're taking the derivative with respect to x. This is the original function. We want to take the derivative with respect to x. Right, so a and b are constants. So when we take the derivative, we're going to do 2 multiplied by a, x, is x squared, 2 minus 1 is 1. It's the derivative of the first term. Then the second term, you might say 3b squared, right? But actually that is a constant, right? b cubed is a constant, and we're taking the derivative with respect to x. So the derivative of a constant is 0. So our derivative should be 2ax. And they've included 3b squared. So this is false. Right, so again, this is like kind of tricky. You just get caught up in the moment. You're like, yeah, let's take the derivative of b. Don't do that. Remember, he's trying to trick you. Okay, so this one, if f of x is a strictly increasing function on the interval 1 to 5, then a right-hand Riemann sum of f of x over 1 to 5 will be an overestimate of this integral. Okay, so for these, I had one student email me about this, and so I drew this picture that might help you guys once it stops lagging. Okay, so if you're looking at right-hand sums and left-hand sums, strictly increasing, strictly decreasing, or increasing and decreasing, these are kind of like your rules. Don't memorize these. That's such a waste of time. But you should be able to, like, if I told you to draw this, you should be able to draw it. So really try to understand it. So when we have a right-hand sum over a graph that is strictly increasing, going off the right-hand points. When we draw rectangles based on those right-hand points, our graph our integral ends up being a very large overestimate, or even like a small overestimate, whatever. But here we can tell clearly that we're accounting for way more than the graph actually provides. That's all an overestimation. Okay, so that's when it's increasing. When it's decreasing and we're going off the right-hand points, it's going to be an underestimate. Here's all the space that we're not accounting for. All right, and then if it's both, it's increasing, then it's decreasing, then it's increasing, decreasing. We don't know. We can't say for sure, right hand or left hand, if it's going to be an overestimate or underestimate. Now it's going to be the opposite for the left-hand side. If it's an underestimate, it's strictly increasing. If it's increasing, it's an underestimate because we're going off those left-hand points. So we're not accounting for some area underneath the curve. Opposite for decreasing, we're going off the left-hand point, it's going to be an overestimate. And if it's both, again, we don't know. Is it an overestimate or underestimate? We have no clue. We can't say for sure. All right, so I can include this in my notes, but this is like a good visualization of overestimation, underestimation based on right hand or left hand. Okay, so for this one, strictly increasing, so that means it's going this way, right? I would just kind of like sketch this out. Then a right-hand sum. Okay, so if we want to make some rectangles, right-hand sums, we're going to go off the right-hand points. Here's one rectangle, here's another rectangle, here's another rectangle. We have the space above the curve that we're accounting for. So this looks like an overestimation. So it seems to me, for like thinking like 1 to 5, that seems pretty legit. It's going to be an overestimation. So again, don't memorize that a right-hand sum strictly increasing overestimation. Like that's not going to help you in the long term. You want to be able to sketch that out and realize, okay, it's an overestimation because I can see it's above the curve. Okay, now if we go the other way, if a right-hand sum over 1 to 5 is an overestimation, then f of x is strictly increasing function. Okay, so this is basically the opposite of our last question. First question is telling us that if it's strictly increasing, then it's an overestimation. Number 7 is telling us that if it's an overestimation, then it's strictly increasing. If you go back to this thing I drew, nope, not this one. Okay, this one. If it's an overestimation, that doesn't necessarily tell us that it's strictly increasing, because it could be both increasing and decreasing and still be an overestimation, right? So this one actually looks like it might be an overestimation because we've got all this area above the curve. Even though we've got some area underneath the curve that we're not accounting for, we've actually got more area above the curve. So I would say that this one is probably going to be an overestimation. But it's not strictly increasing, it's decreasing at some spots too. So basically what that's telling us is that even though it can be an overestimation, that doesn't necessarily mean that it's strictly increasing. But if it's strictly increasing, this is hooked up to my mom's phone, sorry. If it's strictly increasing, we can say that it will be an overestimation. Okay, so this one is false. Next one is, if this integral from 0 to 5 equals 7, then 0 to 5, when it's like the absolute value of the function equals 7. All right, so when the original one equals -7, the absolute value would equal +7. You might be like, yeah, the absolute value of -7 is 7, so that's true. It's probably not going to be that easy, right? So just based off that, I would probably say false. But the reason is that the integral is telling you the change, right? The overall change from 0 to 5. It doesn't necessarily mean that it's displacement, right? So like how far you go is different from how far you went from the first point to the second point, right? So say you're driving a car. This is your starting point. Your distance traveled could be like this to get to the end, but your displacement is only this much. That's kind of like a concept you have to realize, that distance traveled doesn't always equal displacement, or no, distance traveled. So it's kind of that same concept here. If your distance, I don't want to mess this up. Basically, some of your original function could be above and below the graph. And so if you add them up, it's -7, just because you take the absolute value doesn't mean it'll be +7. There's no correlation there, right? You don't know if your distance traveled was the same as your displacement. So that might not make a ton of sense. I feel like I didn't explain that super well, but basically this is definitely false. First, just I can tell based on the way it's worded, it's just too easy. But also, when you take the absolute value of your derivative function, that doesn't necessarily mean that your integral is going to be the absolute value of what you got. Okay, here's a pretty common one. If you have the plot of the function q of x, what is the correct derivative of q of x? Derivative is the first, like the first prime. So if you think of a derivative, that is a plot of the slopes. So your y-axis is slope, your x-axis stays the x-axis. So we know that, I would say here, when you look at your original graph, make sure you label it. Is it the derivative graph? It's the original, like just make sure you're super clear what graph it is. All right, next I would look for the minimums and maximums, because those are our critical points. Critical points are when q prime x equals 0. So if we find those critical points, looks like I have one at 2. I definitely have one at 4. Might have one somewhere over to the left, but probably won't use it, so I will leave it alone. 2. So all we need from that information is that at x equals 2 and x equals 4, we know q prime x equals 0. When we have minimums or maximums, we have critical points. That tells us the derivative is equal to 0. So when I look at derivative functions, derivative graphs, I want to see where does the graph cross the x-axis. Where does the graph cross the x-axis? So you know that's when it's equal to 0, and that will probably be the derivative graph. At least it's like one step in the right direction. So x equals 2, x equals 4. Looks like here it crosses at 1.75, so I'm going to rule this one out. Here it crosses at 2 and 4, so that one's good. This one is 1.75, cross it out. This one's 2, 4, that one's good. All right, so now we have a 50-50 chance. And yes, the first graph is q of x, the original function. And they tell us that in the question. All right, so we know where the critical points are. What's our next step? Next thing you can do is try to figure out, is the derivative negative or positive? You don't really need specific numbers, but you can figure out, is it going to be above the x-axis or below? So I would see here, if we're going from 0 to the first critical point, looks like we're decreasing, right? Our slope is going downwards. So this is a negative slope. So we can tell just based off that alone, our graph has to be A, because this is where it's below the x-axis, it's negative. Remember, our y-axis is kind of like slope here. So if it's below the x-axis, below 0, that's where it's negative. Why wouldn't x equals 1 be a critical? Okay, so remember, critical points are where the derivative function crosses the x-axis and where the original function has a maximum or minimum. So in our original function, our critical points are where we have maximums and minimums. In our derivative function, our critical points are where it crosses the x-axis. All right, so minimum here, maximum here. This again was our minimum and our maximum. So it depends what graph you're looking at, if you're looking at where it equals 0 or where it has a minimum or maximum. Original function, you're looking for minimums and maximums. Derivative function, you're looking for where it crossed the x-axis. Right, so here we had a negative slope before the first critical point, so it was below the x-axis. Here it's increasing, it's going this way, so it's a positive slope. Therefore, the derivative function must be above the x-axis because we've got positive values here. So that's what separates A from D. And again, you guys remember that when we have negative to positive, that's a minimum. When we have positive to negative, that's a maximum. So that lines up as well. All right. So that one is definitely not the easiest. I know it takes a while to kind of like wrap your head around it, but just review that one too. All right, a small business monthly sales of a new product is given by Q of T equals 2000 T minus 100 T squared units per month, T months after its introduction. Okay, so T is months and Q of T is giving us sales. I like to define my variables. The price that a business charges is given by P of T. So P equals price. How fast is the business's monthly revenue changing 4 months after the introduction? Okay, so we want to find revenue. So I'm going to denote that by R. And we want to find how the revenue is changing. Remember, changing, rate, anything over a value of time, you're thinking derivative. Right? Changing equals rate. The change in 4 months. How is it changing at 4 months? Think first derivative. So R prime. So that is like a super keyword there. Okay, so revenue equals P times Q. That is something you should memorize. I know I'm always like, don't memorize this. Memorize that one. You can't like logic. I mean, I guess you can logic, but like R equals PQ. Revenue equals price times sales. Or quantity, I should say. Think of Q as quantity. They don't necessarily tell us that, but you can think the number of sales you make is equivalent to the quantity. Okay, so they gave us the two Q and P. We're going to multiply them together to get R. So R equals Q. That's 2000 T minus 100 T squared times P. 100 minus T squared. That is our revenue function. We want to find how fast the revenue is changing at a certain time T. So we want to find the derivative of R. 2 ways to do this. You can simplify R by like distributing and getting like a long thing and then taking the derivative, or you can use the product rule. I'll use the product rule so we can get some practice. So we will have f of x and g of x. F of x, I'll make the first one. G of x, I'll make the second one. We'll want to find f prime and g prime. F prime will be the derivative of f of x. So we'll have 2000 minus 200t. G prime will be negative 2t. All right, then we can use the product rule. The product rule is f times g prime plus g times f prime. There are like a few variations on that. They're all the same thing. So we're going to do 2000 t minus 100 t squared times g prime, so that's negative 2t, plus g, that's 100 minus t squared times f, 2000 minus 200t. All right, so that is r prime. I'm gonna move this over. And here we use the product rule. You want to memorize those rules, by the way. Product rule, quotient rule, power rule, you should already know. Chain rule, that one's really important. Those, there's probably a couple more, but those are examples of what you can put on your formula sheet to memorize. All right, where was I? Okay, so now we have R prime. We're almost done. We want to find how the revenue is changing 4 months after the introduction. T is giving us months, so we want to set T equal to 4. So we'll find R prime of T. So I'm going to plug in 4 for T. All right, and then all of that later, we can plug that into our calculators. So 2,000 times 4 minus 100 times 4 squared. So that first one gives us 6,400. Negative 2 times 4 is negative 8. Plus 100 minus 4 squared gives us 84. Multiplied by 2,000 minus 200 times 4. That's 1,200. 6,400 times negative 8 is negative 51,200 plus 84 times 1,200 is 100,800. And so that is equal to 49,600. And so that is how the revenue is changing 4 months after. So that will be dollars per month. Dollars per month, because sales is being given in units per month. And so we'll go another month. Okay, so how did I get there? Remember, it's going to be, our derivative units are going to be the original units divided by whatever the T unit is. And here our T was months. And if you see, our original unit was units per month. Okay, so I did units, which was dollars per month. And then since it's the derivative function, I did another per month. Dollars per month per month. Kind of confusing. That one's not very common. But that will give us our revenue changing. So R prime of 4. Any questions on that one? It's pretty long. Okay. The figure provides the plot of the instantaneous rate of change of a function q of x. Identify the graph, right? That's the first step. The original graph they're giving us is the graph of the first derivative. How do I know that? It's saying the instantaneous rate of change, the IROC. Our IROC is our first derivative. That's like one you should just know. Instantaneous rate of change equals first derivative. Okay, so original graph, or like the graph they're giving us, is the first derivative, and we want to find the original graph. So we want to find the original function. It's kind of like we're taking the integral, right? Okay, so if we're going backwards, you can use the same technique that we did for the last problem we had that was similar. It was like flipped around, and you would just start at the answer choices. So you would find the minimums and maximums and see if they correspond to the critical points. Or we can go the other way, which is what I'll do now, so we can learn it both ways, where we start with the critical points and try to find the minimums and maximums. So critical points on the derivative graph will be where the function crosses the x-axis. So here that's at 1 end at just above 2.5, like 2.7 maybe. Okay, so where it crosses the x-axis, we have critical points. So right away, I can eliminate a couple because we can see we have a minimum here, maximum here. So that one is a maximum of above 3. So I know that one's wrong. Here, the maximum seems to line up. The minimum seems to mostly line up, so that one's fine. Here they line up again, that one's fine. Here they don't line up, this one's above 3 again, so I'm going to cross this one out. All right, so now we want to see, do we have a minimum or maximum at 1, and do we have a minimum or maximum at 2.7? So we can actually find this straight from the graph because we know when it's above the x-axis, our slope is positive. When it's below the x-axis, the slope is negative. When it's above, it's positive. So it's kind of like we're using the first derivative test on the graph itself. When it's positive to negative, we have a maximum. Therefore, we have a maximum at 1. So we know that B would be correct. Here we can see we have a negative to positive, negative to positive, that's a minimum, right? So at 2.7, we have a minimum. Again, B is the right one. So soak that in. It's basically going the other way from our first question. So you can kind of go either way since it's a multiple choice test, but I would know how to do it both ways. Okay. Suppose a business's profit 2 years after 2013 is modeled by P of T $1 million. Market research determines that P prime 3 equals -4 and P double prime T equals -1. This means that at the start of 2016, which are the answer choices? Okay, so this one's like a little tough. You have to really think about it. It's a concept question. So the profit is modeled by P of T. The market research determines that at 3, so 3 years, our rate of change is -4. And our, I kind of think of it like acceleration, but our second derivative is -1. So based on the answer choices, the way they're worded, I would think of it just in terms of like negative and positive. I wouldn't really worry about the numbers. So our first derivative gives us the marginal profit, and they're telling us that this is negative. They told us it's -4. Don't worry about the 4, it's just negative. The double prime, or the second derivative, is the rate of change of marginal profit. Remember that the second derivative is the rate of change of the first derivative. Again, they told us it's negative. All right, so first derivative is the rate of change of the original function. Second derivative is the rate of change of the first derivative, so on. Right, you can do third derivative is the rate of the change of the second derivative. So that would be the rate of the change of the rate of the change of marginal profit, which is the rate of change of profit. All right, got it? So derivative is rate of change. I think you would have made that clear. Okay, so at the start of 2016, which is 3 years after 2013, that's why they told us P of 3. What is our business's profit doing? All right, so we know that it's negative, right, for the first derivative. So we know that if our first derivative is negative, the original function is decreasing. It's going this way. That means our profit is decreasing. Decreasing. This type of question is kind of known as a 2x2 because you can see increasing and decreasing and then less and less and more, so we can eliminate half of the choices. We know for sure the profit is decreasing. It's not increasing. We know that because our first derivative is negative. If we look at our second derivative is telling us how the first derivative is changing. So the first derivative is changing in that it's becoming decreasing. It's like decreasing, becoming more negative. So profit is decreasing. Let me sure I said this right. Okay, yeah. The profit is decreasing more and more. It's negative and it's becoming more and more negative. So the profit is decreasing, and then at the rate of which it's decreasing, that is also decreasing. Okay, so it's already negative. Second derivative is telling us that it's actually becoming more and more negative with time. Okay, so that one's, again, kind of tough. Okay, graph of f prime x. Remember, we want to identify the graph. So this is the first derivative. I always write this really big. Just please get in the habit of doing this. It will help you. So we want to find the minimum of f of x. Okay, so we are given the derivative graph. We want to find the minimum of the original graph. So we're going to look for critical points. That's when the graph crosses the x-axis on the derivative graph. So we have 1 at 2, 1 at 6. It could be either of these. It's definitely not going to be anything else. So we can cross out everything else. All right, so cool. Now we have a 50-50 chance. We want to find the minimum. Okay, so again, we can kind of use like the first derivative rule. When it's above the x-axis, the slope is positive. When it's below the x-axis, the slope is negative. Again, above is positive. So if we're going up, then we're going down, we have a maximum. If we're going down, then we're going up, we have a minimum. So we're looking for the minimum, that's going to be at x equals 6, because our slope is going down, and then at 6, it changes to going up. So E, yep. Okay. Consider f of x equals e to the power of 5x. For what value of x is the function's instantaneous rate of change 100? Okay, so here I would look at taking the derivative, because instantaneous rate of change, you should automatically think derivative. First derivative. And we want to find when the first derivative equals 100. So the x value at which f prime x equals 100. First step is to find f prime x. So we have f of x equals e to the power of 5x. In this case, you're going to use the chain rule. This one, like with the e to the power of whatever, I kind of just memorized this, but we'll go through chain rule anyways, because the less you have to memorize, the better. But chain rule, we choose one. I'm going to do a and b. We're going to choose two variables to use the chain rule with. You can do, like traditionally, it's f of x and g of x, but I prefer a, b, because it's not as confusing with the f of x we already have. So the first function you choose is going to be the outside one, right? Remember chain rule, we have like an outside and an inside. Our outside one is e to the power of x. What's inside that x is 5x. Then we're going to want to find the derivative of both. So a prime equals e to the power of x. Derivative of e to the power of x is just e to the power of x. B prime is going to be 5. Then we use the chain rule, which was a prime of b times b prime. Yeah, I'm pretty sure that's the chain rule. Like I said, I don't really have to memorize it because I'm lucky enough to be done with this class, but you should memorize it. Okay, I'm pretty sure that's it. Okay, so chain rule, that will give us f prime x, and then we have a prime, which is e to the power of x. Instead of x, we're going to put in b, so we'll have 5x, and that's times b prime, so that's 5. So f prime x equals 5e to the power of 5x. And we want to find when that equals 100. So we're going to set that equal to 100. Now I'm going to solve for x. So I'm going to divide both sides by 5 to get e to the power of 5x equals 20. And then I'll take the natural log of both sides to get rid of that e. So I have natural log. The natural log is going to get rid of the e. So we'll be left with 5x equals natural log of 20. Divide both sides by 5. We get x equals natural log of 20 divided by 5. and we get 0.599. That's equal to 0.6 if we round it. So final answer is 0.6. I'm gonna move this over. Shoot. Okay. Now we want to find another limit. That's super fun. Okay, so limit when you have h approaching 0. This is the limit of the difference quotient. It's also how we used to find derivatives back in the day before we had all our fancy rules. And so for this one, whenever you have the limit of the difference quotient, I really want you to think about simplifying the expression as much as possible before trying to evaluate it. So simplify first whenever you have something like this. It's going to become so much easier to evaluate. So we have 9 times 3 plus h squared. So first I'm going to FOIL out that 3 plus h squared. So 3 plus h times 3 plus h. 3 times 3 is 9. 3 times h is 3h, plus that 3 times h is 6h. And h times h is h squared. So that's what that expression is. That's all multiplied by 9 minus 81 over h. So all I did was expand it a little. Now I want to distribute that 9 out. So we have 81. 9 times 6 is 54. So plus 54h. And then 9 times h squared is 9h squared minus 81 all over h. You're going to, what's it called? Simplify like terms, combine like terms. There we go. 81 minus 81 is 0. So we end up with 54h plus 9h squared over h. Now all of our terms have an h in them, so we can divide that h out. 54h divided by h is 54. 9h squared divided by h is 9h. All right, so this simplified is this. And now we can rewrite the limit because it's so much easier to solve now. Limit as h approaches 0 of 54 plus 9h. All we have to do now is plug in 0 for h. So we get 54 plus 9 times 0, and that will give us 54. Final answer. All right, so remember, biggest thing with these is to simplify it first. Otherwise, you won't get anywhere. All right, the following table, oh, by the way, it is past 1:30, so if you have anywhere to be, you're totally free to go. And of course, I'm still recording, so I'll post it. But yeah, stick around if you have nowhere else to be. So the following table shows bicycle production in millions of bicycles. Find their average rate of change between 1950 and 2000 and give units. Right, remember, average rate of change is different from instantaneous rate of change. Average rate of change is kind of like our secant line between 2 points. Instantaneous rate of change is more correlated with the derivative. So the exact rate of change at a certain point, otherwise known as our tangent line. So secant line is kind of like average rate of change. Tangent line is more instantaneous rate of change. So average rate of change, they're going to give us an interval, and we want to find the difference between those two. So we're looking at 1950 to 2000. All right, so remember, average rate of change, you want to use the difference in y over the difference in x. So rise over run. So I'll do y1 minus y2 over x1 minus x2. You can also do y2 minus y1 over x2 minus x1. It's the same thing. So when I plug in my values, I have 2 points here. One point is 2,231. So that's that point right there. And our other point is 1950, 21. So we're going to use those 2 points as our y1, y2, x1, x2. So y1 can be 2000. Oh, no, that's x, sorry. Y1 can be 231. There we go. And y2 will be 21. x1 will be 2000, and x2 will be 1950. Plug that in the calculator. And that gives us 4.2. So that is the average rate of change of bicycle production between those 2 years. The units, remember, average rate of change kind of has the same units as derivative. It's like a rate. So that's going to be your original unit divided by your t value, or like your t units, which was years. So we have bicycles per year. You can also think of it like we divided y by x. The units of y was bicycles. The units of x was years. Bicycles divided by years. Bicycles per year. Okay, oh, this one is pretty common, the fencing problem. We're gonna keep using this one, so get familiar with it. Charlie is fencing a rectangular play area for his lucky dog. One side of the fence will be the house. So this side, we're not gonna worry about at all. We don't need any fencing for it. One side of the fence will be composed of chain link, that's C, which is $8 per foot. And the remaining 2 sides will be wood, which is $5 per foot. See the figure below? I don't know why you couldn't make it all the same material, but whatever. Charlie would like to spend a total of $160 on fencing materials to determine the maximum area. Right, whenever you see maximums in derivatives, maximums in calculus, maximums or minimums, think derivative. Max, min, think derivative and set it equal to 0 so you can find the critical points. Okay, so let's set up some equations, make a system of equations and solve for that, and then find the maximum area. So one thing I can figure out is how many feet of fencing will I have? And then we can figure out how much we're going to spend on the fencing. Other thing I can figure out is how to find the area. I feel like the area is the easiest of the two, so I'm gonna do that first. The area of a rectangle or square is going to be width times length. So here I have W times C. Area equals W times C. That's just like a general formula. Our other formula can be how much we're going to spend on the fencing material. So we know total we want to spend 160. And we know that we have $8 per foot of C and $5 per foot of W. And so we can think 8 times C will give us the total cost of that side of the fencing. So 8C, that makes up part of our cost. Other part of our cost is the cost to make the 2 W's. We have 2 W's, right? So plus something times 2W, because we have literally 2 sides that are W. And each one is going to cost $5. So I'm going to multiply that by 5. Okay, so it's like 5W times 2, or 2W times 5. You can think of it either way, but basically it's going to be $5 per W, and we have 2 W's. So that is going to give us our total cost. I can simplify that. 160 equals 8C plus 10W. Okay, so now we have 2 equations. We want to find maximum area. So I want area to be our base equation so we can take the derivative of it. Why did we set up 2 equations? I can't take the derivative of area right now. It has 2 variables in it. It has W and C. I only want one variable, W or C, so I can take the derivative of it. That's why we have 2 equations. Okay, so I feel like no one really explains that to you. We have 2 equations so that we can substitute into area to get it in terms of one variable, so we can take the derivative and find the maximum. So what I'm going to do is simplify or rearrange that $160 equation so I can get it in terms of one variable, and substitute that back into area so I can get area in terms of one variable. So I'm going to isolate for, say, W. So I'll do 160 minus 8C divided by 10, and that will give me W. So all I did was get W alone. Moved 8C over, divided everything by 10. Now I can take that W, let's change colors. take the W and put it back in here so I can get area in terms of just C. Oh gosh, okay. So I'm going to take area equals W, which is 160 minus 8C over 10, and that will all be multiplied by C. And so that will be area equals 16C minus 0.8C squared. Yeah, I think so. Okay, so all I did there was divide by 10, simplify, distribute that C out. You guys can do that again too, but all I did there was simplify. And then how I got here was by substituting. Substitute. Okay, so now I have area in terms of one variable, C. I could have also gotten it into W's, right? Doesn't matter. I just wanted to get it into one variable. All right, so now I want to take the derivative so I can find the maximum area. If I set that derivative of A equal to 0, I can find the minimums and maximums, the critical points. So I'll take the derivative, I get 16 minus 1.6C. Set that equal to 0 so I can find critical points. So 0 equals 16 minus 1.6C. Move the 1.6C over to the left. And then we'll divide both sides by 1.6. I think we get C equals 10. Yes, we do. Okay, so C equals 10. Now I could go back and find W, but I really don't need to. All I need to do is find the maximum area. C equals 10 has told me that when C equals 10, that's when our maximum area will be. That's when our area will be maximized. So all I can go back and do is plug in that 10 for our area formula, this one right here, and I'll find the maximized area. So if I plug that in, our maximum area will be when C equals 10. So 16 times 10 minus 0.8 times 10 squared. And that will give us area of 80. The units are feet squared. Okay, so area equals 80 feet squared. That is our maximum area. If you'd gone the other way and you wanted to check your work, W ended up being 8. Just FYI. If you had wanted to solve for C and then plug that back in, and then you would have gotten area in terms of W, then the same thing, you would have gotten W equals 8. Okay. Losing stamina. It's cool though, almost there. The figure below provides students velocity v prime t in feet per second, t seconds after she begins riding an electric scooter along a straight road. Use the figure to calculate an estimated f double prime 1. Using units, interpret the meaning of your answer. Okay, so we're going from f prime t to f double prime t, or 1. So in that case, we're going towards the side of the derivative. So always think of it like f of x to f prime x to f double prime x. If we're going to the right, it's a derivative. If we're going to the left, it's an integral. All right, so in this case, we're going from f prime, because that's our graph that's given, and we're getting to f double prime, because that's what they're asking us to find. And so we want to find f double prime of 1. Okay, so when we find a derivative based off a graph, we're looking at the slope. So we're looking at x equals 1, and we want to find the slope at that point to find the derivative. Okay, so like I said, we're going from f prime to f double prime. We're taking one derivative. That means we're going to find the slope. And so we're finding the tangent line, the slope of the tangent line at x equals 1. Sorry, t at 1. p equals 1. Okay, so I'm going to draw a tangent line. I'm going to try to draw a tangent line. So I did that by drawing 2 points really close to 1 and then trying to get a line between the two. This is definitely going to be hard to do on an exam, so I hope he doesn't ask you to do it to this extent. But now I want to find the slope. Remember, slope is rise over run. In this case, I'll just choose 2 points and then use that y1 minus y2 over x1 minus x2 formula to find the slope. Average rate of change, same thing. Okay, so here I see a point here that's 0, 7, so I'm going to use that point. Also looks like I'll just use a point here. So we have 2 point, oh my bad, looks like 3.75, and that's, okay, wait, that's the y value. 3.75 and our x value is 1. Okay, so I chose 2 points on the line, and then I'm going to use the formula to figure out the average rate of change. So I will have 7 minus 3.75 over 0 minus 1. And that will give us 3.25, but make it negative because we end up with a negative denominator. So negative 3.25. Go back and check to make sure this makes sense, right? Because our slope is downwards, right? It's negative, we're going down to the right. So we know that's definitely going to be negative, that makes sense. Looks like it's going down about 3 units per every 1 unit to the right. That seems cool. So f double prime 1 equals negative 3.25. Okay, let's put that here. All right, now I want to find the integral. Okay, so now we're going the other way. We're going from f prime x to the original, no primes, just f of x. We're going to use a right-hand sum with n equals 4. I'm actually going to change colors completely. Okay, so n equals 4 tells us the width of a n equals 4 tells us the number of rectangles. Change in x tells us width, n equals number of rectangles. That one's pretty important. That's just like notation to memorize. Okay, so in this case, they're giving us n, that's the number of rectangles. They want 4 rectangles. And we want to estimate it from the interval 0 to 8. All right, so 0 to 8, it's going to be from here to here. Pretty easy. 4 rectangles. So from 0 to 8, I'll probably do a width of 2. So I'll have 1 rectangle from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. They want a right-hand Riemann sum, so we're going to use the right-hand point to form our rectangles. So in this case, I'll use 2, 4, 6, and 8. At 0, that's the left-hand side, so I'm not going to use that. However many rectangles you have is however many points you're using. So remember that. Okay, I'm going to draw my rectangle. So 4 rectangles. To find the Riemann sum, I want to find the area of these rectangles. A Riemann sum is estimating the area underneath the curve. So basically just remember, find the area of the rectangles, add them up. That gives you an estimation of the area underneath the curve. Just kind of like going back to the original function. Okay, so the area of each of these, this looks like about 2 times 1, because remember this change is in 2. Change in x is 2, so 2 times 1, the area of a rectangle is width times length. So 2 times 1 is 2. Here it looks like this might be 0.75. So 2 times 0.75 is 1.5. Here it looks like we have a y value of 3. And so 2 times 3 is 6. And then here this might be 2.75. So I'll be 2.75 times 2 is 5.5. Yeah, 5.5. Okay. We want to find the area underneath the curve. That means adding up all the rectangles. So 2 plus 1.5 plus 6 plus 5.5 is 15. I can actually write that out. Okay, so 2 plus 1.5 plus 6 plus 5.5 equals 15. We want to interpret the meaning of the answer using units. So we're looking at the change in the original function from 0 to 8. Original function looks like it will be how many feet she traveled, because they're giving us the velocity as feet per second. So if we want to go back from the velocity to position function, we're going to take away that time component and we're left with feet. So in 8 seconds, 8 seconds, she moved 15 feet from her starting position. Okay, so this is kind of when I go back to, wait, let me make sure this is correct first. Okay, they got 14 feet, so estimation error, whatever, but yeah, 14, 15 feet. Wouldn't we multiply by 2? I don't see where we would multiply by 2, because we already did multiply by 2. So you can actually also do this by doing 1 plus 0.75 plus 3 plus 2.75, and then multiplied that by 2. And that would also equal 15. Those are two different ways of doing it. As I calculated the areas, I was multiplying by 2. The way you're thinking is probably using the y values, then multiplying by 2 at the end. Both work. Probably my way is actually a little bit longer, but I feel like you don't get as confused. It's like a little bit simpler to think about. But yeah, that's probably what you're thinking of. We would multiply by 2 there. So you can either multiply by 2 as you're calculating the areas, or at the end, same thing. So in this case, this is giving us the displacement, okay? So when we look at the integral over an interval, that is displacement. Again, displacement is how far you travel from the original starting point. Right, distance traveled is different. In this case, our distance traveled is equal to our displacement because she was going along a straight road. But if it was like a curvy road, our displacement would be different. So in this case, we can also say that it's the distance she traveled. But if you want to be like perfectly precise, it is the displacement. Think of the interval as the integral as the displacement. Okay, any other questions on this one? Okay. 2 more. Which of the following is correct for p of x equals square root of 3x plus x squared? And we want to find the derivative of p of x at x equals 1. First thing we're going to do is take the derivative of p of x. So p prime of x equals, all right, whenever I have a square root, cube root, whatever, fourth root, I like to turn it into an exponent form so we can take the derivative. So I'm going to rewrite the original function as 3x plus x squared to the power of 1/2. Right, now I want to take the derivative. This looks kind of tough. Looks like we have something inside another thing. So I'm going to use the chain rule. So we already did this once today. I'll set 1 equal to a, 1 b. And so a is the outside function. Remember, always the first function you do, whatever you label it, is the outside function. That's x to the power of 1/2. Our inside function will be 3x plus x squared. Let's find a prime and b prime. A prime is 1/2 x to the power of negative 1/2. B prime is going to be 3 plus 2x. All right, now I'm going to use the chain rule. So that is a prime of b times b prime. So a prime is 1/2 x to the power of negative 1/2. And inside that a prime, instead of x, we're going to put in b. So we'll have 3x plus x squared. And that'll be multiplied by b prime. So remember, use parentheses here, 3 plus 2x. All right, so we don't have to simplify because we're going to plug in 1. So it'll just kind of be like a waste of time. Don't bother with that. We want to find p prime of 1. So p prime of 1, I'm going to plug in 1 for x. All right, into the calculator. 3 times 1 is 3, plus 1 is 4. 4 to the power of negative 1/2 is 0.5 times 0.5. So this first component is 0.25, or 1/4. And that is going to be multiplied by 3 plus 2 times 1, that's 5. So 1/4 times 5 is 5/4. C. So we took the derivative using the chain rule, made sure to turn it into exponent format first, and then plugged in 1 for x to find the derivative at 1. All right, use calculus to find, I like how they specify that. Use calculus to find and classify any extrema of b of x equals that function. All right, so classifying extrema. Remember, extrema are critical points or maximums and minimums. So first thing to do is to take the first derivative. All right, so derivative, we can just use the simple power rule for all of this. Negative 1/3 times 3 is negative 1. And then we have x squared. We can actually take out that 1 and just leave it as negative x squared. Then we have plus 36. Derivative of 123 is 0. So that's our derivative formula. And then when we want to find critical points, we set that equal to 0. So 0 equals negative x squared plus 36. I'm going to move the x squared over to the left. And then take the square root of both sides. Square root. So we'll get x equals plus or minus 6. Remember, when you take the square root, don't forget plus or minus. Okay, so those give us our critical points, which are potential maximums and minimums. Classifying means to determine, is it a maximum or minimum? So I would actually move this over. Extrema are critical points. Classifying means figuring out are the maximums or minimums. So here I use the first derivative test. I'm going to put in negative 6 and 6. Negative 6 and 6 are two critical points, and we want to classify them. So we're going to figure out, is the slope negative or positive on either side of them. So I'm going to start with a value less than negative 6, plug that in for my derivative formula, and figure out, is that positive or negative? So something less than negative 6, let's go negative 10. So I'm going to do b prime negative 10 equals negative 10 squared plus 36. All right, so negative 10 squared is positive 100. Remember, whenever you're squaring a number and that negative is within the parentheses, it's going to end up being positive, because negative 10 times negative 10 is positive 100. Then positive 100 times that negative that's outside the parentheses gives us negative 100 plus 36. Negative 100 plus 36 is definitely going to end up being negative. I honestly don't care what number it is. I just care, is it negative or positive? It's clearly negative, so I'm going to put a negative right here. All right, next we want to choose a number between negative 6 and positive 6. I will choose 0. So we have b prime 0 equals negative 0 squared plus 36. 0 plus 36 is positive 36. Don't really care about the 36, but it's positive. So here between negative 6 and positive 6, the slope is positive. The derivative is positive. The last one is a number above 6. So I will choose b of 10, b prime 10. This is going to basically give us the same thing as b of negative 10. 10 squared is 100. Negative 100 plus 36, again, is negative. All right, so we have negative, positive, negative. If we look at negative 6, if we're going down, that's negative. Going up, that's positive. We get a minimum. If we're looking at positive 6, to the left, it's positive. To the right, it's negative. So that is a maximum. So negative 6 is a minimum. Positive 6 is a maximum. Those are our two critical points. Minimums and maximums classified. Okay, so we made it to the end of the worksheet. Oh my gosh, finally. Honestly, it took less time than I thought it would. If you guys have any questions, I'm totally open, as many as you have. And the final, I believe, is all multiple choice. Is it not? I got 2 questions about that just now. You know what? Whatever I say, don't make sure you fact check it, because maybe it's not. Yeah, you guys are welcome. I thought it was, but I don't know what I'm saying, so maybe it's not. Yeah, you're welcome. Yeah, if you guys have questions, this recording is also going to go up on YouTube. I'll post my notes, so you guys are welcome. I'm happy. I hope it helped. I definitely hope you guys do well. Good luck. It's great working with you guys. No questions. And Kevin, if you have anything. You might be asleep, I don't know. I usually sleep through my classes. But yeah, I'll end it here.